In this lecture, we're going to look at seismic attributes. In this example on the right, you see a seismic reflection section for different geological circumstances for an incised valley. On the right is the seismic section, and in the middle over here is the interpretation of that. As you can see, the seismic reflection on the boundaries of the valley is much stronger than the reflections inside the valley, as for example in here. So clearly the rock properties and the change in acoustic impedance is substantially different in the boundary than in the layers inside the valley. So given an image like this, how do we characterize this geology from the seismic data? The way we do this is using seismic attributes. So let's take a look at what seismic attributes there are. We can break up seismic attributes into multiple classes. In this case, you're seeing 6 different seismic attribute classes. And there's also advanced seismic attribute classes that we'll talk about in the next lecture. So the seismic attributes in this table are common attributes that are used by the industry. And each class of attribute is unique in its own characteristics. And we're going to talk about all of these classes in this lecture. As you can see, depending on what category the attribute is, it has different types of attributes you can extract. And on the right-hand side, you can see how it's used in the interpretation of the data. So, for example, if you're looking for structure, faults, fold, you would actually look at geometrical attributes. If you're looking at reservoir properties such as porosity, hydrocarbon indicators, you would look at instantaneous attributes or amplitude or AVO attributes. And if you're looking at things like layer thickness and stratigraphy, you would look at spectral decomposition. So we're going to go over each one of these attributes. The first thing to do on an interpretation project before you try to extract any attributes is to pick your structures or your horizons. And from this, you can already do a lot of things and prepare yourself to do the attribute work. So the first thing we do is we pick horizons. And in your projects that you're going to be working on, this should be a sequence of things that you actually do on them. Given different horizons, you would pick these horizons. And then the first thing you would look at is if this is an offshore seismic data, you would look at the water bottom. The reason for this is in the water bottom, the velocity is always going to be increasing. The water layer is going to be lower velocity than the sediments. So you would expect a positive polarity at the water bottom because the velocity contrast is increasing. So you want to check that the polarity at the water bottom is indeed positive. And if it's negative, it means that your seismic data polarity has been reversed, and you need to multiply your data by -1 to get it to a positive polarity at the water bottom. Picking the water bottom is extremely easy because it's a very strong reflection. So if you want to practice your picking skills in the software that you're using, you should first pick the water bottom. And once you're comfortable with how the software works, you can pick other horizons. Once you do have a horizon, you want to be able to display it in map view so you can see what it looks like. So you would want to look at the feature of the software that displays that horizon in map view. The other things you can do is you can fix the geological age and see the deposition spatially. And you can also take a horizon that's not flat and flatten it and then look at the burial history above and below it, the onlapping, etc. So these are the basic interpretation skills that you would want to apply to your project before you actually use this to extract attributes. One other thing you can do is if you know where your reservoir is and you have a top horizon and a base horizon, you can look at the variation from top to base and map the thickness of your reservoir. And you can convert that from time to depth to see in depth where the thickest part of your reservoir is, which you should also be doing in your projects. So let's start, given that you already done this preliminary work, you have your horizons, you mapped them. Let's start by looking at different attributes. So the first class of attributes we're going to look at is instantaneous attributes. And for understanding instantaneous attributes, we have to understand what the amplitude spectrum and the phase spectrum of the seismic data is. So as we discussed earlier, the amplitude spectrum of the data is formed of the range of frequencies that are in your data. So for example, on the left, if you have only two low frequencies, you would have very low frequencies in your data, and that would form a very wide wavelet. As you add more frequencies, in this case 4, in this case more than 4, and etc., if you have a whole suite of frequencies, in this case, for example, almost 0 hertz to say 35 hertz, and you stack that, you're going to get a very tight wavelet, as you can see here, which has much higher resolution. So if we look at this in the spectrum domain, as we said earlier, if you have only the low frequencies up to here, you're going to get a very wide wavelet. And as you add more frequencies into your data, you're going to get a much sharper wavelet. So this is the amplitude side, but there's also a phase side. So the phase is basically the timing of each frequency arriving at that particular location. So in this case, uh, every frequency from low frequency all the way to high frequency is all lined up at time 0, as you can see. And when you stack this, you get this wavelet over here. So this would be the case up here where the phase, we call it 0 phase. So for each frequency down here, the data has the same 0 phase, and you have this addition that ends up in this positive 0 phase wavelet, which is depicted over here. This is time 0. So the question becomes, what happens as you change the phase? And as you can see, if you change the phase of every um, frequency uniformly, so here we went from 0 phase to a certain degree phase shift for all the data, you see that the event is still arriving at time 0, which is right here. But now, instead of having this shape, which is bell kind of shaped, you have this shape where you have a peak on the left, a 0 crossing right at time 0, and a trough on the right. If you continue to change the phase, so here you've changed the phase 180 degrees, then you still have a similar bell-shaped wavelet, but now the maximum value is a negative value. So you basically take an A and multiplied it by -1. You can look at it that way as well. And if you continue changing the phase, you're going to get a similar case as B, but in this case, again, it's going to be 180 degrees shifted. So a minus is going to be a plus, and a plus is going to be a minus. And if you rotate it completely 2 pi, then you get back to case A. The other thing you can do is, instead of varying the phase of every single frequency the same amount, you can actually gradually vary the phase for different frequencies. So on the bottom, you see this case A, which is equivalent to here and equivalent to here. But now what we're doing is, instead of varying all the frequencies at once, we're gradually increasing, changing the phase of the different frequencies. And as you can see, what this does is it actually shifts the wavelet. It doesn't change the shape of the wavelet, but as you can see, it's moving away from time zero to the left. Time zero is over here. It's moved to the left, whereas in the initial case, zero phase, it was aligned at time zero. So what you're doing here by linearly increasing the phase is you're actually shifting the data. You're not changing the wavelet shape, but you're actually shifting the data. So how do you see that in this display? Is that if you, like I said earlier, because you've changed the phase of the different frequencies, you basically shifted them, and then when you sum them, you're going to get this 90-degree phase shifted wavelet, as in case B. So that's what the phase shift is doing to your data. Now, one thing we want to talk about that we've mentioned before is the vertical resolution, which is dependent on the wavelet frequency content. So if you have low frequency, you're going to have a larger a resolution issue, whereas if you have more higher frequencies, this vertical resolution will be less of an issue. But if we have two reflections, and if this is our wavelet, when we convolve the wavelet with the reflections, this is what we're going to get in here. And in this case, this is well resolved, because for each reflector, you can see the peak amplitude over here, as you would expect from this wavelet. So this situation is fine. But if these reflections get closer to one another, so if you have a thinner reservoir, as you move these closer to one another, these two wavelets are going to start interfering. The trough of this wavelet is going to interfere with the peak of the other wavelet. And what you can see here is, now instead of two events, you're getting one event with a wrong amplitude. And if you get even closer, you're actually going to get a one event that has an amplitude that actually looks kind of similar to a single event over here. So this could cause problems in your interpretation, because instead of seeing a thin reservoir, you would see the top or base of another reservoir, and you could misinterpret that. So it's important in an interpretation project to calculate the vertical resolution, which is this Rayleigh criterion over here. That's the wavelength of the wave divided by 4. So lambda, the wavelength, is the reservoir velocity divided by the central frequency of your wavelet. And then it's a quarter of that. So that distance you calculate using your reservoir velocity, the central frequency in your data, divided by 4, would give you the vertical resolution that you're going to have in your seismic data. And you can also use software to be able to calculate something like this. So here you can see what we call a wedge model, where we have an overburden, an underburden, and a reservoir. And all we're doing is keeping the reflection coefficients on the top and the base the same, but varying the thickness from right to left. So over here, there's no reservoir, and over here, there's a thick reservoir. And then we look at the amplitude of the seismic data and plot the amplitude at the bottom. And as you can see, the seismic amplitude is increasing, it's reaching a peak, and then it's decreasing, and then it's stabilizing. So this location over here is where the seismic amplitude is correct for this reservoir. And if you're interpreting this amplitude over here, this is not representative of the reservoir, and you're going to make a mistake in your attribute calculations. So I just wanted to note that before we go into looking at these different instantaneous attributes. So let's talk about how do we compute instantaneous attributes. And we have instantaneous amplitude, instantaneous phase, instantaneous frequency, and instantaneous quadrature. And again, as I said earlier, all we're doing is we're looking at different properties of the wavelet here. So if we take your recorded trace, we call it x as a function of time. This is your trace that you recorded. Um, if we add that the complex component of yt, we would get the u of t, which is the analytical trace. So your question is, yes, we recorded x of t, but what is y of t? How do we get y of t? And what y of t is what we call the Hilbert transform of x of t. So if you take x of t, you multiply it by 1 over pi time, you would get the y of t that goes in to this equation. It also turns out that the Hilbert transform of the trace is actually the 90-degree phase shifted version of that trace. As you saw earlier, the 90-degree phase shift moved that bell curve to a positive negative looking wavelet. So we can plug the y of t into this equation, extract the x of t, so u of t is given by this definition. So to get the analytical trace, you would put your trace in this equation and calculate u of t. Now from u of t, we can express it in polar coordinates as a r and a phi. So this is amplitude and phase of u of t. And we can calculate the r of t as x square of t plus y square of t square root. And this turns out to be the instantaneous amplitude that we talked about. The reason it's instantaneous is we calculate this for every time step, and we can display it for every time step. That's why it's called instantaneous. Um, and this is actually the envelope of the trace, or envelope of x of t. And this is correlated to reflectivity and energy of the reflectivity of the seismic data. Um, so this is related to, for example, bright and dim spots. The second value here, the phase, is actually the imaginary part of the logarithm of u of t, u of t being the analytical trace, and this is the instantaneous phase, this component over here. And this is related to continuity of events. So if you have discontinuity of events, the phase is going to jump in the time direction. And that's what we're trying to track here. So this can give you information about like pinch outs, faults, on-lap, prograding reflections, etc. And then given the R and the phase, we can calculate something called an instantaneous frequency, and that's the change of the phase with time, how fast the phase is changing in time. And that parameter, the WT, can give you information about the frequency attenuation. So if you have frequency attenuation due to, for example, gas being in the medium, that will attenuate the seismic data. You may be able to see that in the instantaneous frequency. One more parameter that's calculated from this type of data is the instantaneous quality factor. And you can see that's the instantaneous frequency divided by the change in the instantaneous amplitude, or the envelope. So you're looking at a ratio of the instantaneous frequency with the amplitude. And what's being done here is trying to get to a parameter that emphasizes a certain thing. So this basically is correlated to local variation in attenuation, and it emphasizes the instantaneous frequency attribute. And again, it's indicative of gas in the reservoir, or some material that actually absorbs the seismic amplitudes. So another one that we can use is called sweetness attribute. And over time, as you can see, people have taken these different attributes and combined them in ways to emphasize something they're looking for. And this one is used for to detect clean, thick reservoirs. So there's a thickness component to it, and if they're hydrocarbon filled. So you're dividing an amplitude attribute with a frequency attribute. And if the amplitude is high and the frequencies are low, that's going to further increase the value of this attribute and uh, help you see certain features in the data more pronounced. So let's take another look at this quadrature data. And as we saw earlier, as we change the phase at 0 degrees, let's say we have a peak or a trough. And then as we change the phase, we can go to a case where we have a 90-degree quadrature of the original 0 phase data. And this actually can be a useful display on its own. So just taking your seismic data, which is 0 phase, and applying a 90-degree phase shift could help you in the interpretation alone. This is an example of how that would work. So if you have a top and a base reservoir, and let's assume in the top you're slowing down, and as you come out you're speeding up, so you have a -1 on the top and +1 on the bottom. If you convolve this with your 0 phase wavelet, you're going to get a trough at the top because it's minus, and a peak at the bottom because it's plus. And if you just look at this, it's hard to correlate visually what you see in the seismic data with what's actually happening in the Earth. By doing a 90 degrees phase shift, you would get yourself into this situation. And just looking at it visually, this correlates much better with what you're seeing in the Earth versus what you're seeing in the seismic data. So this is what we call a poor man's inversion. If you quickly want to look at your data and see where reservoirs are or where formations are, you can actually apply a quick 90-degree phase shift and look at the data that way and try to see if there's reservoirs in your data. So this could be very valuable rather than looking at the 0 phase data. So here's an example of the seismic trace. This is xt, and then once you run those calculations, this is the instantaneous amplitude, instantaneous phase, instantaneous frequency, and then using these, you can generate other attributes like we talked about, like sweetness or something like that. And you can see as the seismic data is going in depth, the amplitude is actually the envelope of the seismic data. So even if it's negative, it's going to go positive and draw this envelope over here. And then the phase, as you can see, as you go down, it's changing. And then in some locations, you see a jump in the phase, like here, or in here, or in this location, you can see that jump. And this location over here, you can see that jump, which indicates some form of discontinuity in the data. And that's what the raw attribute calculation looks like. And then you can display that for all the traces. So here you can see on the left, the original bright spot seismic. So bright spot means this is a low velocity medium. Which means it's got hydrocarbons or gas in it. And as I said earlier, you got a trough at the top and a peak at the bottom. If you were to display this with 90-degree quadrature, you'd basically see a filled area in here, which would be easier to spot on the seismic data. And on the right, you see the instantaneous amplitude, instantaneous phase, instantaneous frequency, and smoothed frequency. So you can see immediately that the instantaneous amplitude, which is the envelope of this thing on the left, kind of shows you a pretty strong change in amplitude that's easier to spot in the instantaneous amplitude. So this is similar to doing a 90-degree phase shift, but it's actually better than that in the sense that you're looking at the envelopes of the positive and negative part combined together. And then in the next one, you're seeing the instantaneous phase and the phase change at this reservoir level. You could also potentially interpret it as spotting these discontinuities in the data, which the instantaneous amplitude is not going to see, obviously. So it's looking at more where the discontinuities are. Um, so that's basically how we use these, I would say, very simple preliminary attributes to take a quick look at the data and identify locations of interest in the seismic data. The next class of attributes we're going to look at are, we call them geometric attributes. And these attributes are basically not looking at the amplitudes as much, the amplitude changes as much, but they're looking at discontinuities in the seismic data like faults, blocks, and these kind of features. So the geometric attributes, the way they work is instead of looking at the trace in time, they're looking at the trace away from that location spatially in X and Y. So they're comparing the trace at one location at that time to a trace at another location at the same time. So if there's a discontinuity between those two traces, they're trying to detect that by taking the derivative laterally of the traces from a particular location. So these can be kind of put into two categories, coherency and curvature. So coherency is mostly the rate of change laterally, which is a derivative, and curvature is if you have a surface, how much it's bent, basically. So this is a slide where it shows an application of coherency to a seismic data. This is a map view or a time slice, if you like. And on the left, you see the amplitude of the time slice, what the amplitudes are. And then if you take a lateral, as shown in here, a lateral derivative of this thing, you basically get the map on the right. And as you can see, this is showing discontinuities. The minute you have a discontinuity laterally or vertically, it's going to pick these discontinuities up, and you can see this over here. So the amplitude feature is gone, and now you have where the discontinuities are. That's what the coherency does for you. And you can see very, very clear faults and areas of deformed zones. This is a salt body over here from this attribute. So the point is that this is an independent attribute from amplitudes that can substantially help in your interpretation. So this is one attribute you definitely want to run on your data. And this is showing the explanation of if you have a discontinuity, the coherency is going to basically disappear, and you're going to get very incoherent measure, which is going to spike at that location. And on the right, you're seeing the coherency on the top and the amplitude attribute at the bottom. And now you can see that there is potentially some hydrocarbon deposition in here, and it seems like it's in this channel where you know the boundaries of the channel and the location of that with respect to the structure of the channel in this particular example. Looking at curvature, the curvature is looking at basically if you have a surface, how curved that surface is. So at the flat parts, you're going to get zero curvature, or this crossing point, you're going to get zero curvature. And when you have this curved event, you're going to be able to fit a sphere at that location, and you're going to measure the radius of that sphere, and that's going to give you your curvature. So it's highly curved, you're going to get a small radius, and if it's flat, the radius is going to be very large. So this is a display of that on the right. On the left is the coherency that we saw earlier, and then on the middle, the B is the most positive curvature, and on the right is the most negative curvature. And you can see that it is showing somewhat similar patterns to the coherency, but it's also dividing into the positive and negative components. You can see that there's a lot more information in these sections over here, but I would caution that some of these may lead to over interpretation. It's very hard to see. And here you can see where the channel boundaries are and where the channels are. But here it makes it very hard to isolate where the channel is and where the boundaries are. So you could start over interpreting this kind of attribute. Um, so there's an explanation of how to use the curvature. I wanted to include this in the slide set. So if you like, you can kind of spend more time on looking at how it works and how you can use it in your data. So now that we looked at discontinuity and we looked at curvature, the other thing we can look at is if you have a surface, you can look at the dip and azimuth of that surface. So this is another structural attribute that takes your surface over here and it looks at the dip and the azimuth of that surface, where is it facing. And this is another simple calculation that you can run once you pick the surface, you can run on your data, and it could indicate different features on the data. And so here's is showing for this particular surface, the dip and the azimuth of that surface. And you can also calculate that and display that. So this is a look at some of these geometrical or continuity attributes. And you see correlation, semblance, weighted correlation, and covariance. The point I want to make here is that if you're looking from one attribute to the other attribute in this class, as you can see, you don't see a lot of variation if you're using specifically correlation or semblance or weighted correlation or covariance. They're pretty much producing the same result. So there's no need in this particular class, there's no need to run a whole suite of attributes. If you just run one, you get the general picture. And then if you're really doing in-depth interpretation, you can run some others and see if they give you some more detailed information or not. But the the thing that defines this class is that it's a continuity attribute. So you have to do this, but just doing one of them could be sufficient to get you initially where you want to go. Um, the next class of attributes that we're going to talk about is amplitude accentuating attributes. And these are similar to the instantaneous attributes, except instead of running at one time step or instantaneously, like in the instantaneous case, we're actually running these attributes in a window and summing those values. So if you have a horizon that you picked in your project, what you can do is you can actually define a window around your horizon, and you can sum the amplitudes that you picked in that window. So if you want to compute, for example, the mean amplitude, you could sum n number of amplitude values and divide it by the number that you summed. Or you can compute the RMS amplitude, which is squaring the amplitude, summing, and then square rooting it, or the average energy, which is squaring, summing, and then divided by the n, as you can see here. What I would highly recommend is from the amplitude side, if you look at this class and the instantaneous amplitudes class, the best thing you can do on your data is to run the RMS amplitude. And this x1 to xn, you would want that from the quarter of a wavelength left to your peak to a quarter of wavelength right to your peak, so that you can capture the maximum amplitude available in your wavelet. So this is an attribute just like one coherency attribute. This is one attribute you should definitely run on your data. And to run this, you're going to have a horizon, because you're going to run this in a window around your horizon. So if you run this class of attributes, this is what that may look like. So here's the RMS amplitude. So you pick the horizon, you pick the window around the horizon, positive, negative window, and you run this attribute to kind of stack the energy at that window. and that's the RMS amplitude. The other things you could do is you could just pick the maximum value in that window instead of trying to sum the amplitudes. And it could be a maximum trough or a maximum peak. Then you can run other things like average energy. So this is basically similar to the envelope attribute we saw before, but instead of giving you the envelope at one time step, it's averaging the envelope over the event that you picked. And again, my main point here is that in this class of attributes, although there's some variation between these different pictures, they each on their own kind of tell you what's going on already. So I would prevent myself from getting confused by running all of these things. I would probably run first the RMS amplitude on that event of interest, which I would probably be able to detect from quick scanning of the instantaneous attributes, and then generate this and compare it to the one coherency attribute that I calculated. And that could give you a pretty good idea of where the strong amplitudes are, and if there's channels that make those amplitudes happen, or if there's some other structure that makes that amplitude happen. So this would be the basic things that you would want to do on your project: to run your instantaneous, to run your coherency, and to run your amplitude, RMS amplitude attributes, and map those, and just start with that to work on your project. Now, the next level of attributes is what we call AVO attributes. And AVO attributes are using another level of complexity, which is looking at pre-stacked data. So all the previous things we were looking at was on stacked data. So you stacked all the offsets available in the data. But in this case, we're going to split the offsets into offset groups and look at these similar attributes we looked at before, but in different offset groups. So your question is probably going to be, why would I do such a thing? Why would I bother? And the reason we would bother is that, as we talked about earlier, when you send an incident P wave in two half spaces like this, you're going to get a reflection of the P wave. And this reflection of the P wave, the amplitude of the reflection of the P wave, is going to depend on the incidence angle. And that equation is given on the right over here. So the reflected P wave at an angle theta, which is this angle over here, this alpha 1p, has this formula on the right over here. And it turns out that the P wave reflected at a certain angle is a combination of the P impedance, the S impedance, and the density. So obviously the P impedance contains certain information on the formation, the S impedance contains additional information on the formation, and the density contains even more additional information on the formation. And in the rock physics lecture, we went over this difference in the information contained in the data. So if we can invert for P impedance, S impedance, and density, we would know much more about the rocks and the fluids in them. And this is why we're interested to look at this pre-stack seismic data, or we call it AVO data, amplitude variation with offset data, to try to understand more quantitatively the rock properties and the fluids in the rock properties. So let's take a look at a publication here that shows the shale and sand trends with depth. So on the left, you have depth, and on the right, you have porosity. So obviously, if a rock is more porous, it's going to be softer, and if it's less porosity, the P wave velocity, S wave velocity, and density are going to increase. So porosity is inversely correlated with the velocities and density. But what happens is, as you pile up more rock on top of more rock, the rock is going to compact. It's going to get harder, and the porosity is going to decrease. But this is dependent on what type of rock you're compacting. So if you have a sand, a clean sand, the porosity is going to change slower Whereas if you have shale, and if you start stacking shale on top of each other, it's going to flatten faster, and it's going to lose porosity faster. So at some point, even though shales initially have higher porosity, at a certain depth, the shale is going to have less porosity. And if you reach a certain temperature and a higher temperature, you're going to get chemical changes in the rock as well. So this is going to cause chemical compaction, as you can see over here after this value over here. And suddenly you see a large change in porosity in the sands due to this chemical interaction, and also in the shales, but not as large. So this trend starts to reverse after a certain depth. And here you can see a display of that in terms of the rock type. So here you have smectite rich shale. Then once you pass the 70 degrees and it gets hot enough, you got elite rich shale. And for the sandstone on the above, you have unconsolidated sandstone. And then with the temperature reaching those higher temperatures, you get consolidated or cemented sandstones. So this is pretty important because, as you can tell, the rock properties changing with depth is going to change your velocities for the sands and the shales, and it's going to give you a different response as you go in depth. So let's take a look at this a little bit. Let's assume we're in the unconsolidated sandstone scenario. And in this case, the sandstone velocity is going to be lower than the surrounding shale velocity. So here the shale velocities are higher and the sandstone velocity is lower. And if we take this rock and we take out the water and put hydrocarbons in it, which are going to be lighter fluids or gas, the velocity is going to even drop further. So you've gone from a water-filled case to a hydrocarbon-filled case, and the velocity has changed. So what does that mean in terms of our seismic data would be the question. If you change the fluid from a heavy fluid to a light fluid, the density will decrease. We're not changing the porosity here, we're just changing the fluid type. And if we look at the definition of the P-wave velocity, bulk modulus, shear modulus, and density, the shear modulus is not going to change. We had talked about this earlier. The bulk modulus is going to decrease, and as we said, the density is going to decrease. So this is going to be the ratio of this is going to basically change, is going to have your P-wave velocity decreasing. So this is important to keep in mind, just kind of a back of the envelope thing, is that if you go from a heavy fluid to a lighter fluid, your P-wave velocity, you should expect that to decrease. And vice versa, if you go from a light fluid to a heavy fluid, your P-wave velocity should increase. So you should really be aware of that. What happens to the shear wave velocity? Well, the shear modulus isn't changing, but the density is dropping a little, as we said. So that's going to make the shear velocity go up a little. So it's interesting to see that if you put a lighter fluid into the rock, the P wave is decreasing, the shear velocity will be increasing. So the acoustic impedance is Vp times density. So this is lower, this is lower. So the acoustic impedance is really going to drop for this case. And the VP-VS ratio, VP is going down, VS is going up, but because it's the inverse, this is really going to go down as well. So you're going to get a large VP-VS ratio change as well. What happens in the consolidated tight sandstone case? Well, this doesn't change because we just looked at what the fluid did in the pore space. So on the right, the shale velocity is low and the sand velocity is high. But as you put the different fluid, this is going to go to the left again. It's going to basically drop for acoustic impedance. And the VP-VS is going to drop as well. So for the unconsolidated case and the consolidated case, the velocity in the rock is going to drop. So now next question becomes, what happens to the impedance contrast? So the impedance contrast is a contrast between the shale and the sand. And in this case, you're going to get a very large negative impedance contrast at the top of the reservoir, where in this case, you're going to get almost no impedance contrast at the top of the reservoir. And the reason for this is that the sandstone is tight sandstone, so it's hard. So it's a faster velocity or impedance than the shale. But when you change the fluid, the impedance drops to around the value of the shale, and you would hardly get a reflection in this scenario. So it's important to understand what the sand is going to do when you change the fluid, and what the relationship between the sand and shale is, to understand what kind of behavior you're going to get for the acoustic impedance and the VPVS ratio. So let's take a look at this in a particular case. On the horizontal is the acoustic impedance, and on the vertical is the VPVS ratio we just talked about. And in this case, we have the shale trend over here. So this is burial and compaction. And as the shale gets buried, the impedance is going to increase because it's going to be harder rock, right? Density times VP are increasing. So this is increasing. And then this is the 100% brine saturated sandstone line. So as same as it gets buried, the sandstone is also going to increase in acoustic impedance. And what's going to happen is we're going to now look at what happens to the sandstone if we take out the brine and we input lighter fluids. So both, as you can see, going from brine to oil to gas, the acoustic impedance is decreasing, and the VPVS is also decreasing. So if we look at this previous case, that's what we expect: AI to decrease and VPVS to decrease. And that's what's going on over here. As you change the fluid in the sandstone, this is decreasing. So that means that the contrast between the shale and the sandstone is going to change as you change the fluid. It's going to go from this location all the way to that location, and you're going to be on a different sandstone line, and that's going to give you an opportunity to detect by cross-plotting the acoustic impedance with the VPVS, an opportunity to detect if the rock is full of brine, oil, or gas. And this is what the AVO method is all about. It's cross-plotting using that pre-stack angle-dependent reflection coefficient data we talked about, trying to get to that P and S impedance, or acoustic impedance and VPVS ratio, and trying to see if we see this kind of fluid trend in the seismic data. So if we look at this as a function of depth instead of porosity as acoustic impedance, as you can see over here, as the rocks get buried, the shale is moving with a higher acoustic impedance, moving along this line, and eventually the acoustic impedance is lower than the sand, which is initially lower acoustic impedance and higher porosity. And as you bury it, you're going to cross over with the shale at some point, and then you're going to have a higher acoustic impedance for the sand versus the shale. So as we saw earlier, we had the unconsolidated case over here and the hard sand case over here. And if we go back to that situation, one would be in this class and the other would be in this class. So you have to be a bit careful about which class you're in. So the industry has basically said that if you're in this hard sand over here, we'll call this class 1. If you're in this situation over here where you're crossing over and your shale and sand velocities are more or less the same, we'll call this class 2. And if you're shallow, if you're in the unconsolidated sand case, we'll call this class 3. And as you can see, the class 3 over here is going to be the easiest to see because it's going to make a much larger impedance contrast with the shale, whereas this class 2 or deeper class 1 is going to be much harder to see because it's going to have a very similar reflection coefficient as the shale. So these would be the easy to detect plays from the seismic data, or reservoirs to detect from the seismic data. And these would be a little more challenging to detect from the seismic data. So if we look at this as far as logs are concerned, again, we have depth here. So compaction is starting and then cementation, as we said, due to the temperature change over large temperature, the rocks are becoming consolidated. And as we said earlier, you have your class 3 up here, and you can see it's a negative reflection coefficient. This is 0, no reflection coefficient. And this color is showing you brine, oil, and gas. So if this is brine filled, as you saw earlier, in the unconsolidated case, the velocity of the brine filled sand is about the same as the shale, so you get a very small reflection coefficient. But as you put lighter fluids, you get a larger negative reflection coefficient, which is easier to detect on the seismic data. This horizontal axis is offset here. So that's dominated by the VPVS ratio. And as you go further offsets, you get a much more dipping situation, whereas with brine-filled sand, it was flat. So this change from going flat response to dipping response and being more negative can tell you that you have an oil-filled sand versus a water-filled sand. So let me repeat that again just to be clear. If you have both in this unconsolidated section, if you have both an increase in the negative reflection coefficient and an increase in the gradient, that would indicate that you have lighter fluid. And if the gradient is flat and you have a small reflection coefficient, that would indicate that you have a water-filled sand. So you can use this to uh, estimate what kind of fluid is in the pore space at these depths. And then this is class 1 and class 2 over here. As you can see, class 1, class 2 almost has a 0 reflection coefficient, but you can also see that the dip of water versus the dip of gas can be a bit different. So you could use this discrimination of how fast the gradient is to determine what kind of fluid is in the pore space. And this is what we do in the industry. So if we look at this plot, like we said, class 1 is over here, class 2, class 3 and 4 AVO. This is a synthetic seismic data generated for those different classes over here. So for example, in class 3, you have a negative reflection coefficient. So this is going to be negative with offset. And then you can cross plot, just like we did acoustic impedance and BPVS, you can cross plot the intercept, which is this value over here, and the gradient, which is the rate of change of this slope. You can cross plot these things, the intercept and the gradient. And the background trend is going to be along this line over here. And if you have a gas or hydrocarbons in the pore space, you would divert from the background trend. So your intercept and gradient would change from the background trend, and you would be able to see the class 1, class 2, and class 3 distributions in this AVO space. So all you really need to do is you need to, for each location, you need to compute your intercept from the seismic data, and then you need to compute the gradient. Then you can cross plot it, and if it's away from the background trend, it could be a good reservoir. And this is an example of that being done on field data. And here you can see these locations where you see this anomaly away from your background trend. And these would be locations where you might want to put some wells and test and see if they're productive reservoirs. So let's move on now to seismic inversion. In AVO, when we looked at AVO or when we looked at the amplitude attributes, we just took the data as is and looked at these things. The other thing we can do is we can try to invert the data, meaning we want to go from reflection coefficients into velocities and densities. That's what the inversion is all about. So if we go back to this equation here, we said that the reflection coefficient of angle is a function of P impedance, S impedance, and density. But these are contrasts in P impedance, S impedance, and density. And we talked about this earlier in the lectures, is that the seismic data doesn't record the actual P impedance, S impedance, and density in the formation. It records the changes in P impedance, S impedance, and density. So what we're trying to do is to go from this changes in information into the actual P impedance, S impedance, and density values of the reservoir. So like we said earlier, the poor man's inversion is just applying 90-degree phase shift, and you're going from contrast to actual reservoir changes. This is not a real inversion. It's just a quick and easy way to look at the data in a couple of minutes. You can do this thing on your data and see it much better in terms of the reservoir properties themselves versus the changes. But then you can do what we call a post-stack seismic inversion. So if the data is stacked, and assuming that there's not much AVO in the data, you can assume that the stacked data represents P impedance changes and invert that P impedance changes into P impedance. And then you can do a pre-stack seismic inversion. So this would be equivalent to the AVO thing we looked at earlier, but instead of looking at intercept gradient kind of parameters, we're actually trying to get the P impedance and S impedance out from that equation you saw earlier. And the reality is that we can't really invert for density because we don't have large enough offsets in the seismic data. And then we can use P waves and converted waves, which we haven't really talked about too much in a joint inversion. And we'll talk about that a little bit later here. But it helps you get a better shear impedance that you can get from P impedance, P waves alone, and maybe gives you some information on the density. And then we have something called a geostatistical inversion, which basically statistically generates impedances and then generates the seismic data and matches it to the field data. And if it doesn't fit, it just iterates on a different model and scans a whole range of models to see what's going to match your seismic data. So to be able to do this inversion, we do need to know the wavelet because we're trying to take the wavelet out of the equation. So we do need to know what the wavelet is. And if we're doing it on pre-stack data, we need to know what the wavelet is as a function of the angle gathers or reflection angles. And we estimate that from the seismic data. The other thing we need is a low frequency model. So like, as we know, the seismic measures the response from some low frequency to some high frequency, but there's always a gap between zero frequency and the low frequency in the seismic data. And because we don't know this, we have to generate this to be able to do this inversion. And we generate this from well logs. We take well logs and we get the low frequency P wave velocity, S wave velocity, and density. And then we interpolate that throughout the field to use at every XY location for this inversion process. And the method we use is usually called constrained sparse spike inversion. There's other methods of inversion as well, but it's kind of a model-based inversion as well, where you're modeling and trying to match your field data, making some assumptions on sparseness of the reflection coefficients. Here's a result of post-stack versus pre-stack seismic inversion. So on the left, basically these letters here are wells, and at the wells you can see the impedances from well logs. So all we need to do, for example, to get the P impedance, which is what we're looking at right now, is take the P wave velocity from the well log, the density from the well log, and multiply the two. That's P impedance. So there's your actual P impedance over here. And on the right, you see the scale here from 4,000 to 12,000 meters per second per gram per cc. And you can see zones where you have low impedance, and you can see zones where you have high impedance. And on top of that is displayed the inversion result for P impedance. And on the bottom, you see a second section. There's two different locations, 2D lines that are taken from the inversion volume. And then on the right, you see again the P impedance, but this time from the pre-stack inversion. So um, as you can see here, for example, look at the match at this top chalk zone over here. You can see a much better correlation between the P impedance from the well and the inverted P impedance from pre-stack data versus the P impedance from the well and the inverted P impedance from the post-stack data. As you can see, the post-stack is showing a much larger impedance value than the well, and the P impedance from the pre-stack data matches the well log a lot better. Um, so there is absolutely very good value in using pre-stack data for your inversion project if you have pre-stack data. Now in our course, the lab study we're going to do is only post-stack data. So we'll only be looking at post-stack data. And in this class, will not be doing inversion because this is a very lengthy and tedious process, and we won't have time to do that. But it's good for you to understand why you want to do pre-stack inversion versus post-stack inversion. And this is just looking at zones where the pre-stack inversion is much better than the post-stack inversion. Okay, and here's an example of pre-stack inversion. But in this case, we're showing the P impedance and the S impedance. Remember, with pre-stack data, we can get both P impedance and S impedance. So this is the display of P impedance and S impedance. This is a different location or project than the previous project, but I just want to show you that you can actually get two different parameters from the pre-stack inversion. And then what we can do is we can actually convert those to mechanical properties of the formation. So by simply taking the P impedance and S impedance, which is VP rho and VS rho, we can convert those to, for example, lambda and mu, lambda parameter and shear modulus, or we can convert it to Young's modulus and Poisson's ratio. The trick for Young's modulus is you also need density. You see the density term here? You also need explicitly density to be able to do this conversion. So if we look at the equations, I can get P impedance and S impedance. Instead of IP in this particular publication, it's ZP, and instead of IS, it's ZS, but that's P impedance and S impedance. And I can convert those impedances to lambda mu and and moduluses using these formulas. If we want to do this process, we need to find what density is. And as I said earlier, this is hard to estimate from the seismic data. So you can have a workflow where you take the density from the wells and you distribute them into the model away from the wells using neural networks. And then you get the P and S impedance from the seismic data and use that to estimate Young's modulus. So it's a bit of an approximate estimate because, you know, the density you really aren't inverting for everywhere. You're just extrapolating from the wells. But this is one way to go over to Young's modulus and Poisson's ratio. And in this particular project, we see that this kind of information can be valuable for predicting TOC, or total organic carbon, in the rock. So if we look at Young's modulus versus Poisson's ratio from well log data, we see that when you have a lower Young's modulus, you have higher total organic carbon in the rock. The Poisson's ratio doesn't really matter that much for this. And also, if you have more carbonates, you get a larger Young's modulus. So you want high TOC and high carbonate, so there's going to be a sweet spot in here that you're going to want to extract and put your wells in. So we've done that study, and based on the previous plot, we've mapped those locations as ductile to brittle, and moderate changes in between where you have brittle rock, but you're also productive. And those are the locations where you would want to put your wells based on this pre-stack inversion and converting that to modulus properties. You can also use this information for thickness mapping. So these are much thicker zones than these zones over here from the inversion. And you can use that to identify the best areas to drill your wells, and also use those properties to build a static and dynamic model. So we talked a little about using P waves and converted waves. Most of the time, if we have 3-component or 4-component receivers, we will record the converted waves. So in addition to PP reflections, we will also have PS reflections. As we saw earlier, the PP reflections have P wave velocity, S wave velocity, and density, or P impedance, S impedance, and density. And the PS reflections will actually have density and shear impedance. So if we have both of these data sets, we can actually do a better job at inverting for P impedance, S impedance, and density. And that's the value of having the converted wave data. So you can get more stable and more parameters out of your inversion process. The inversion workflow becomes more complicated, of course. You have to have your gathers, which we talked about earlier. Gathers means your pre-stack data at different offsets. And then, like we said earlier, you have to form a low frequency background model now for P and S waves. And then you have to extract your wavelets. As we talked about earlier, you need the wavelets to be able to do an inversion. And the wavelets for the P waves will be different in frequency content than the wavelets for the PS or converted waves. And then we would do a joint inversion of PP and PS, similar to just doing a PP inversion, but this will be jointly inverting those two equations. And then from that, we would get P impedance, S impedance, and density. And then from this, we can get lambda rho, mu rho, Young's modulus, Poisson's ratio. But now, instead of having to try to interpolate the density from the well log, we can actually get it from the seismic data, which will give you much more reliable elastic properties. In addition, potentially, in addition to Young's modulus, Poisson's ratio, also the density parameter. Um, now let's take a look at PP pre-stack inversion versus joint PPPS pre-stack inversion on a particular project again. And here we're looking at VP over VS, which is more related to the shear impedance inversion parameter. It's a mix of the P and shear impedance, but it's kind of like the second parameter, which is harder to invert for. And we basically see that, for example, these zones over here, these sections over here, there's some false or bad information in the PP pre-stack inversion on the VPVS ratio, whereas the joint inversion has cleaned those up. And you can see some good correlation between well-estimated VPVS and the calculated VPVS. If we look at this in terms of correlation with well logs, this is a different project. If for P impedance, we see that if we just use pre-stack P wave data, we get a 0.7 pretty good correlation with the well log. 1 would be perfect correlation. And using PS with PP doesn't really change that very much, because the P impedance can be extracted pretty accurately from P-wave data alone. So that's only a 8% change. But look at the S impedance. Before, the S impedance was about 0.6, and now it's going to about 0.7. So you can see about a 20% improvement in S impedance. And as we said earlier, and for density, it's very hard to get density from P data, and you can see it's a very bad correlation of 0.3. And then with joint PPPS, we've raised that to 0.55. Now, this is a big change. It's about a 45% change. But again, 0.55 is not a great correlation. We would want this to be 0.7 or higher to be able to rely on the density inversion. And this is going to depend on the offset range we have. The larger offsets we have, the better we can do with the density inversion using both PP and PS waves. The last thing we want to talk about is spectral decomposition. And this is another way of looking at the spectral components of the data to recognize discontinuities, channels, but in more depth or detail than just looking at coherency. So this is looking at spectrally decomposing the data. So the red is 5 Hertz band, the green is a 25 Hertz band, and the blue is a higher frequency 65 Hertz band. And we give different colors to these frequencies, and as the frequencies get closer, we change the color map. And here you can see, if you look at it, you can see different features in the data that may be a little bit harder to see on coherency data, a little more depth in the resolution in terms of, you can see this meandering channels in here and over here. And you can see this lobe structure in here. You can see stacked channels in here. So this gives you a little more depth and a little more understanding in the data, but it takes a little bit more effort to generate this attribute and display this attribute compared to coherency, which is basically the simple push of one button to run that attribute. And here's a little bit more information on the spectral decomposition that if you're interested in this, you may want to look at in a little more depth. And here's some examples of the spectral decomposition. So like I said earlier, if you were running a coherency, you'd see a black and white, and you'd see these channel boundaries. But now you can see a lot more detail inside these channels and their spills and how they're meandering in the seismic data. And this is another part where you can actually see the fill inside these potentially deltas kind of structures using this attribute. And also in the sea bottom, which has very high resolution from seismic data, you can actually see these different features in the sea bottom, canyons and beds that are color coded based on these different kinds of attributes that we're running. So what's the strategy for your projects? I want to get back to that. The thing you should do with your projects is obviously first take the data and run a quadrature. And as we said, that's a poor man's inversion. And you can quickly see from that different sections that you may want to focus on. And then you would want to check your polarity and pick your horizons. And once you do that, you can actually run RMS amplitudes in a window around your horizon. And you can also run your coherency attributes and display it on those horizons. And then if you pick the top and the base of your reservoir, you can compute your reservoir thickness and look at that as well to see if it's resolvable or if it's worth drilling. And if you do have pre-stacked data, you can do these aviar cross plots that we talked about. Once you do this kind of scanning exercise to see what's the best locations to drill wells, you would want to go to those locations and run more specific attributes and different kinds of attributes to be able to identify where is the oil, where is the water, and if it's a reservoir worth pursuing or not, based on the things we talked about earlier, like migration, trap, seal, source, these kind of additional pieces of information that you're going to need. So with that, we'll be ending the lecture here. I do want to mention that there is a nice book out there about seismic attributes. If you want to learn more in-depth information, it's by Kurt Marfort through the SCG. You can also um, get that book and take a look at as well. Most software you're going to use is going to have number one, a help, like a tutorial, YouTube type video tutorial that you should probably be watching. And also every piece of attribute you can run will have a help file which will tell you kind of what the attribute is, how it works, and things like that. So you should be looking at those to understand when you look at a certain attribute what it is and what it's doing. So with that, we will end this lecture.